Technically, momentum and energy on the curriculum and on the old provincial exam were actually one big unit. And it was just called conservation quantities, things that are conserved. Momentum is conserved, energy is conserved. Momentum, as I've already probably pointed out, is tougher mathematically. It's nicer in many ways because energy, you had all those different forms of energy, and so even though when we were doing the law of conservation of energy, GG, I was often ignoring what we were losing to heat. I was often ignoring what we were losing to sound or to light. Where momentum, especially linear momentum, it's going to stick around. What you start with is what you end with. There's no other types of linear momentum that it can vanish to. There is something called angular or circular momentum, which is a whole other topic, but that's also conserved. So what we're going to look at, Liam, are questions where we use both conservation laws. Key concepts here. We're going to apply momentum to conservation to collisions or explosions, to juns. We're going to use energy to analyze swings, pendulums, curved heights, if there's a change in height, change in speed, yucky curvy path, or if they start talking about heat, because heat is the work done by we'll get there. And the last thing, which may be obvious in hindsight, for a complex problem, break it down to steps. Here is an example of a question involving momentum and energy. It has a 30-gram bullet moving at 250 meters per second. It strikes a wooden block, which is at rest. Mentally or physically, I'd probably underline the word at rest, and sticks into it. If it sticks into it, what kind of a collision is this? Inelastic. Afterwards, the block and the bullet move off on, let's keep it simple, on a frictionless table, so no ice. Sorry, no heat generated by friction between the block and the floor. A says, write a momentum equation. Can do. B says, find the speed of the block after the impact. In fact, we can find the velocity of the block after the impact. And then C says, find the heat energy created during the collision. Really, what this is asking me to find is the loss of KE. What does KE stand for, Sam? How do I know it's kinetic energy? Everything's flat. I don't see a change in height anywhere. I think I can totally ignore potential energy. But I'm willing to bet if you add up how much kinetic energy the bullet had incoming, and then you add up how much kinetic energy the block and the bullet have afterwards, we probably lost some because the bullet did work force times distance, making the whole, and probably generated some heat on impact. Is that okay? Looking at this question, you ready? Do you see angles anywhere? Oh, thank God. No tip to tail. We can do our momentum straight algebraically. We'll still start out the same way. So A says, write a momentum equation. The sum of all the momentum before equals the sum of all the momentum after. I'm going to use a B for bullet. I'm going to use a B for block. That's it. Oh, how about a W for wood? There. You could also call them mass 1, mass 2. Before the collision, what's moving? The bullet, the wood, both, or neither? So we're going to have the momentum of the bullet incoming. Yes? Wham! They collide. After the collision, what's moving? The bullet, the wood, both, or neither? Both, stuck together, or separate? Momentum, both, final. Now remember, we did this for stuff at angles too, but this right here, once we had our momentum equation written out, we then paused and we said, angles, if there were, we dolped. So I say to you again, angles? Oh, so I can now go to mass of the bullet, V of the bullet initial, equals mass of the bullet plus mass of the wood, mass of both, V final. By the way, that blue line is the answer to A. It said write a momentum equation. There it is. Now we're moving on to part B. Part B said find the speed. I'm actually going to find the velocity. I'll say to the right or something like that. How would I get the velocity of the block and the bullet, the wood and the bullet after the collision? What am I going to solve for here? What am I going to solve for here? I'll give you a hint. One of the V's. VF. Do I need to go tip to tail? By the way, I guess you technically could. This would work as a straight line vector diagram. The thetas would be either 0 degrees or 100. Forget it. We can do it algebraically. Yeah.
If there's something at rest and it's inelastic, there'll never be an angle, will there?
If there's something at rest and it's inelastic, there will never be an angle. Will there? Let me just think. And it's inelastic. It sticks together. I think you're right. Let me ponder and see if there's an obscure, bizarre physical concept where that doesn't happen. So I'll come back to you. I think so. Because the second object has no momentum, so all of the momentum and therefore all of the direction would come from the first object. And so the direction would all stay, even if it came in at an angle, it would go out at exactly the same angle. I think so. Now, that's if we're treating this...
What like a pendulum?
Hold that thought. You mean like that? I know my audience. I'm kind of... So get the VF by itself. It's going to be mass of the bullet, velocity of the bullet initial, divided by mass of the bullet and mass of the wood. Okay. The final speed is going to be, what was the bullet? 30 grams. Is that 0.3 or 0.03 or 0.003 kilograms? How many zeros in front of the 3 after the decimal? Yeah. 250, is that right? Not that fast a bullet. 333 is the speed of sound, so this bullet is subsonic, suggests it's a pistol, not a rifle. Although not all rifles go supersonic either, but this is not a high-powered gun. And is it 5.03? I can do that in my head. Do the rest. This isn't going to work out nice. I get 1.4910. I'll call it 1.5, but I'll use this number later on. Oh heck, 1.49 meters per second. So there, Robbie, is my answer to part B. Robbie, what does part C want me to find?
The energy.
More specific.
Loss of kV, kinetic energy.
Can you read to me what they said, though?
Finding the energy created during the collision.
Which we're going to interpret as, read me the bracket,
Loss of kinetic energy.
loss of kinetic energy. This is a job for conservation of energy. I'll do that on the right-hand side here. Here's letter C. I would start out by saying KE initial plus PE initial equals KE final plus PE final. And remember, this was not on your formula sheet, but if there's heat, we better include heat. Robbie, is everything on a nice flat level ground?
Yeah.
And that's why I said we could ignore the potential, and that's really why I said I think we're going to end up just finding the kinetic energy lost. How would I get the heat by itself, my friend?
Minus the,
And you'll get initial minus final, which is not change in. Change in would be final minus initial. That's why I was careful. I didn't say let's find the change in kinetic energy. I said let's find what we lost. And what you lost is initial minus final. What you started with, take away what you ended up with. So how much heat was generated? It's going to be initial minus final. Now we got to break this down even further. What was moving initially? So this is going to be a half m of the bullet v of the bullet squared minus what was moving afterwards? Both stuck together or separate? Okay, if they were separate, I would have two expressions. I would go bracket. I would put them all inside the minus sign bracket. Here, it's just going to be a half mass both V final squared. Alrighty. Heat is going to be 0.5, 0.03, 250 squared minus 0.5, 5.03. I'm going to write 1.49 squared, but Drake, I'll use my answer button there. I think I should get a positive answer because I suspect I did lose some kinetic energy. Didn't violate the law of conservation of energy. It got transformed into heat and also force times distance, making the hole in the block, applying that force over a given distance. So we should, I hope, get a positive answer. Whew. 932 joules, is that right? Or did I screw up?
No, you're correct.
Yeah? Okay. Did I do the ballistic pendulum with you folks in Physics 11? Okay, so I did this with Physics 12. I don't know if you ever wondered, nowadays, I told you this bullet was traveling at 250 meters per second. Nowadays, in forensics, in crime investigation, we can measure bullet speeds really accurately with high-speed video and all sorts of stuff. What about 60 or 70 years ago, before we had radar, before we had digital technology, how would you figure out how fast a bullet was traveling? It's not like you could time it. Human reaction time would be terrible. How would you figure out if you were the FBI or the RCMP, or if you're just a gun manufacturer and you'd like to know how fast the bullets are leaving your rifle? How do you figure that out? And the answer is you use something called the ballistic pendulum. Okay? You hung a block from a ceiling, and you fired a bullet into it. So here's our setup. We have a bullet coming in, 200 grams. Its initial velocity is 100, which is pretty slow. It's going to hit and stick. And I think what's going to happen is the block is going to swing up. We're going to see if we can calculate how high it's going to swing up. Now, what they did back then is they reversed this experiment. You would do the experiment, you would measure how high the block had swung up, and you could do that with a standard flash photo strobe photography, that technology we've had for about 100 years. You could just expose the film. And then, knowing the height, you could work your way all the way backwards and figure out how fast the bullet must have been incoming. It's quite clever. So we're going to do it going forwards. If you were a forensic officer, you would do this experiment going backwards to figure out the incoming velocity of the bullet. So we have to recognize that there are two events. The collision, right here, and then the swing, right here. Because there's two events, I think I'm going to go divide my page into two. And on the left, I'm going to write and on the right, I'm going to write. All right. Let's analyze the collision. We have B for bullet and B for ballast. Did they?
Why is it called P for pendulum?
P for pendulum? Because then I have P for momentum and P for pendulum. That's not going to be confusing at all. So you ready? How about we call this mass 1, we call this mass 2. Or we could have called it mass A and mass B. No, then I'll get the B for bullet and block mixed up. Is a collision is a job for momentum. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. Before the collision, what's moving? Mass 1, mass 2, both, or neither? Mass 1. Yes? Wham! They collide. Well done. Complete poker face the entire time. Well done, sir. 2 years of permanent emotional scarring, but we do have some success now. Afterwards, stuck together, yes? We could handle this, by the way, if the bullet went through. They would just have to tell us how fast the bullet was traveling after it went through, and we would have a second momentum on the right-hand side. Okay, could. Angles? Later on the swing, angles, but in the collision, angles, or are we in a nice straight line? Straight line. Oh, thank goodness. So I don't have to solve this with vectors. M1 V1 initial equals M1 plus M2 V final. I guess the final speed that the block and the bullet start swinging at is going to be M1 V1 initial divided by M1 plus M2. What was the bullet's mass? 20 grams? 0.02. Very slow bullet. 100 meters per second. Think about that's taking 1 second to go the length of the football field. You'd actually be able to follow this with your eyes if you were quick. So I've made up bad numbers. I stole this diagram from somewhere else. And the bullet and the block, you know what? 4.02. Are you okay, Ty? I added the 4 and the 0.02 together in my head. What's their velocity, or speed, technically, since I'm not including a direction, after the collision? 0.02 times 100 divided by 4.02. You get 0.4975124. I'm going to write 0.498, but I'm definitely going to store this on my calculator. This is not what the question wanted me to find. This question wanted me to find the height. That's right here. Is there a change in height? Yeah. Is there a yucky curvy path? Probably a change in speed. I think that's a job for conservation of energy. KE initial plus PE initial equals KE final plus PE final plus heat. Does the question mention heat at all? No, we're in our magic physics world where everything works out nice then. Okay. Are any of these zeros? PEI, because, not a province. At the top for a split second, you're at rest. So we end up with this. A half m v initial squared equals mgh final. Which mass? Mass 1, mass 2, or both? It is the mass of both, although, do I need to be that careful? What happens to the masses here quite wonderfully? But for what it's worth, it is the mass of both if I didn't want to cancel. How would I get the h by itself? The final height is going to be, it looks like, v initial squared divided by 2 times g. It's going to be this number squared divided by 2 times negative 9.8. No, we're back in Scalarville. 9.8. And I get a terrible answer. 0.013. This swings up like 1.3 centimeters, which it's because I made the initial velocity way too small. You can measure that, but in real life you would get a bigger swing. Okay. 0.01, what did I say? 26 meters. 1.26 centimeters, if you want to quantify it. Well, that much, which is weak. Before you turn the page, stay here. So what they used to do, if you knew the height, if you knew h, could you get v? Times by 2 square root. And this v is the same as this v. So here's my question. If you knew this v, from the height, could you calculate the incoming velocity of the bullet? Divide by the mass of the bullet. That's how it was done. I mean, there's some error, heat and things like that, because in real life there would be some, but still going to be pretty close. How else are you going to do it without fancy digital technology? Yeah.
How do you account for loss of energy to sound?
How do you account for loss of energy to sound? I would imagine that you could run this experiment a number of times with different masses of blocks, and probably if you graphed the difference in height, you might actually be able, you might be able to quantify how much you were losing to sound. I don't know. I'll think about that. Well, and also sound isn't that much energy. I don't think. That's not much there. I don't think. I mean, a bullet makes a loud noise, and I realize that. I'll ponder that. I might do a Google search. How many joules of energy is the sound of a rifle shot? I mean, you can hear it from a ways away.
So there's no set equation for sound?
I'm sure there is. I don't know it. I would suspect there is. Yeah, I think there is, because NASA had to take sound energy into account on their Apollo and space shuttle launches. The engines are so loud. Have you watched on TV a moon rocket launch or a space shuttle launch? Right before launch, all that smoke that comes out is not smoke. They actually dump about a swimming pool's worth of water into there, and what you're seeing is steam, and that water and that steam absorbs a great deal of the sound energy from the air. Otherwise, the heat tiles would get shaken off from the sound Yeah. So that's not smoke, what you're seeing. That massive plume that comes out right by the ground, it's all steam. And I think it's about a swimming pool's worth of water that they dump into there almost instantaneously. And it flashes into steam. Hashtag nerd trivia. How many more am I doing here, Mr. Dewick? Okay, lots more, so I'm not going to finish the lesson today, and you won't get homework today if you finish the homework last day. I'll do all these. Example 3, is there a collision? Yeah. Is there a change in height, change in speed, curvy path? In fact, you know what? I think there's 2 collisions. I think M1 is going to hit M2. It says all collisions are hit and stick, inelastic. And then I think M2 and M1 are going to climb a hill, which means they'll slow down at the top of the hill. And then they're going to collide with M3 and stick, which means they'll slow down after that. I think this question has 3 parts. I'm not going to divide my page into 3 vertically. I'll kind of imagine my page into 3 horizontally. So I'm going to have to deal with this collision, then the hill, then the second collision. Is that okay, Sheldon? I think that's how I'm going to parse this up. So, I've been talking for a while. Let's be bold. Since everything is in a straight line, just this once, let's take some shortcuts. Before the collision, what's moving? Mass 1, mass 2, both or neither? Mass 1, I'm going to say we have M1 V1 initial incoming. I didn't write the sum of, and I didn't write them as P's. If there was angles, I absolutely would. Is that okay so far? Good. Wham! They collide. And stick together, so it's going to be M1 plus M2 V final. If you want to, I'll put a big circled number 1 next to this as I'm analyzing situation number 1 from the diagram. And I think the speed that they're going to move off after the first collision is going to be M1 V1 initial all over M1 plus M2. It's going to be, what was mass 1? Oh, they're all 4 kilograms. That's nice. 4 times 32 divided by 4 plus 4, or 8. All of us can do this in our heads because it's really 4 divided by 8. What's 4 over 8 as a fraction in lowest terms? It's half of 32. In your head, what's the answer? So after the first collision, they're moving off at 16 meters per second. Did I leave you the whole page? Good. Then, for situation number 2, they hit the hill. Is there a change in height? Is there a change in speed? Is there a curvy path? Conservation of energy. Are any of these 0? Are we ever at rest? I don't think so. I think at the top of the hill we're still moving. That's why we're going to collide with the third mass. Are we ever on the ground?
Yes.
Oh, yeah, PEI, because, you know, you've heard my rant. Not a premier, but a mayor. Okay. This is going to be a half m v initial squared equals a half m v final squared plus m g h. Which mass? Mass 1 plus mass 2. In this case, doesn't matter. What do I want to find? V final. I'm going to go times by 2, times by 2, times by 2. That's going to cancel out that 1/2 and cancel out that 1/2. And I'm going to end up with VI squared minus 2GH equals VF squared. This looks very close to VF squared equals VI squared plus 2AD. In this case, though, it's a minus, which makes sense because at the top of the hill, they should be going slower. There should be a minus. Oh, and then square root. V final at the top of the hill is going to be the square root of 16 squared plus 2, no, not plus, Mr. Duick, minus 2 times 9.8. What was the height of the hill? Sorry? 0.82. 0.82. (16 squared minus 2 times 9.8 times 0.82 equals square root of that. Should be smaller than 16. 15.49, is that right? I'll write 15.5. Is that right? Anybody else? Yeah. Which makes sense. 0.82 meters, that's not that big a hill. You didn't lose that much energy going to the top. So you're still going at most of your speed. Now we have situation 3. Before the collision, what's moving? Mass 1, mass 2, mass 3, some, both, neither, all, what? Okay, so it's going to be mass 1 plus mass 2 there, V initial, which I think is going to be the 15.5. Yes? Wham! They collide. And I think they all stick together. So I think the final speed after the collision is going to be mass 1 plus mass 2 V initial divided by mass 1 plus mass 2 plus mass 3. Really, since all the masses are the same, I could have called every mass M. On the top, I could have put 2M. On the bottom, I could have put 3M. Anyhow, I think it's going to be 4 over, no, not 4, 8 over 12, because 4 plus 4 and 4 plus 4 plus 4. I don't think so. Something was nearly over, though. I didn't say that, but thank you for intuiting what I was hinting at. So it's going to be 8 times answer button divided by 12. 10.3. I'm gonna say I like this question. I'm not saying I like. What I am saying is, if I give you a combined energy and momentum question, it will be something like this or the ballistic pendulum, where the collision is in a straight line, but then there's a nice change in height, change in speed. Or, realistically, probably something like roller coasters, because you know I'm kind of nuts about roller coasters. But we're gonna pause here.